Hi, today we're going to continue our discussion about circles by talking about inscribed angles and inscribed polygons. Let's start with a review of what an inscribed angle is. An inscribed angle is an angle that has a vertex on the circle, and the sides of the angle have to at least contain some chords. So the angle could end on the circle, but it could also continue going. And so this is what we call an inscribed angle. I like to think of it as having and you'll hear me refer to it, it's on the circle. The intercepted arc, if you think about the trajectory of a plane, it would intercept the circle at the points inside, or the arc that is created by the two chords of your angle. So those are some interesting vocabulary words that we're going to talk about more today. Let's first just look at some of the ways that inscribed angles and their intercepted arcs can appear in a circle. So I went ahead and looked at the inscribed polygon, DOG, it's a triangle inside a circle. And each of these angles, angle D, is inscribed because its vertex is on the circle and its endpoints are also on the circle. And so we've got angle D is inscribed, angle O is inscribed. If you cover up the rest, you can see that it's inscribed. And then angle G is also an inscribed angle. So there's 3 inscribed angles in this inscribed triangle. And we can name each of them and we can identify their intercepted arcs. So if I look at the first one, which is angle DOG, he's pink. The arc that he intercepts is the arc created by the sides DO and OG, which in this case, come on, Mr. Pin, would be this arc here. That is the intercepted arc that corresponds to angle DOG. Similarly, I can identify the intercepted arc associated with angle ODG, and that would be the arc created by sides DO and DG. And then lastly, I can also identify the intercepted arc associated with angle DGO, and that would be the arc DO created by the sides DG and OG. So that's just an example of some intercepted arcs and their inscribed angles. As with all of our circles, there are lots of theorems that go along with these. Okay, so let's just look at one of them. This one is pretty concise. It says that the measure of an inscribed angle is half the measure of its arc. So what does that mean? That means if I look at this example, and actually I think that's all I have written. There we go. If I look at this example, angle PIG, the orange angle, is inscribed. Its vertex is actually on the goal. And what this theorem says is that the measure of PIG, I should put an M here, the measure of PIG is going to be half its intercepted arc, which is PG in this case. Another way you can think of this, and this is just an algebraic rearrangement, I could say it takes 2 of my angles to equal 1 arc. If I want to actually solve, so that's the geometry, folks. It's just that simple. The angle equals half the arc, 2 angles equals the arc. If my angle is 50, my arc is 100. If my arc is 200, my angle is 100. It's a 2-to-1 relationship. If I want to solve this particular one, I just do some substitution. And you can use either formula, doesn't really matter here. If I use this second one, just because it's here, I know my arc is 120. And I know that I need 2 of my angles. In this case, my angle is 3x minus 3. And from here, I just do some simplification. 6x minus 6 equals 120. 6x equals 126. And so x equals 21. That was it. That's all I had to do to find the value of x. It's that 2-to-1 relationship. If I look at another example using another theorem, this theorem says that if I have two inscribed angles of a circle or in two congruent circles that intercept the same arc. And so this is what's really important here. If they intercept the same arc or congruent arcs, then the angles are congruent. Okay, so let's look at a picture of that. If I look at circle Q, the first thing I notice is if I cover, and I like covering things up when I look at this, and I don't have anything to cover up with immediately. I'm going to use this little makeup box that I find handy. Don't ask me why. Okay, so if I look at this, I've got angle SPT, which is inscribed because P happens to be on the circle, and that creates the intercepted arc created by SP and TP. And so it's pink in this case, 68 degrees. The problem stem tells me that. And then if I look at another inscribed angle, so if I look at angle SRT, I notice that SRT creates the exact same intercepted arc. The intercepted arc is created by chord RS and chord RT. So these two angles, my angle 1 and angle 2, both have the same, they intercept the same arc. And what this theorem up here tells me is that means that angle 1 is congruent to angle 2. Angle 1 is congruent to angle 2, and we know from the previous theorem that my angle measure is going to be half of my arc. So if I want to find angle 1 or angle 2, angle 1 is congruent to, so we can do it all at once, angle 2, which is congruent to half of my arc measure, which we know is 68 degrees. So I can divide 68 by 2, and I end up with angle 1 equals 34 degrees, and angle 2 is 34 degrees. So there's a little trickery going on there, but it's still that 2-to-1 relationship. Okay, let's look at another theorem. The theorem says that if an inscribed angle of a circle, so I've got an inscribed angle, angle FEG, it's inscribed, the vertex is on the circle. If it intercepts a semicircle or half the circle, then the angle has to be a right angle. And so that's going to be handy to know. That means that angle FEG has to equal 90 degrees because remember, all right angles measure 90 degrees. Okay, so how does that help me solve for X in this particular example? Well, I know X is 90 degrees because it's a right angle. I could also find that if you want to know how this theorem was derived, if you think about it, FG is a diameter, and we know that a diameter measures 180 degrees by definition. And we know that angle FEG has to be half the measure of its intercepted arc. So half of 180 equals 90 degrees. I keep forgetting my little M's here. All right, so that's that theorem and an example of how to use it. Super straightforward there, but it can get a little bit more complicated. So if I look at this picture, wow, look at all the information I was given here. It's a little bit nutty. I went ahead and identified and drew in some pieces here. The first thing I recognize is that PS is a diameter. That means by the theorem up above, angle PTS is going to be a right angle. I also note from the question stem that chord or arc PQ is congruent to arc RS. And so I went ahead and marked those. And then if you look, I'm going to cover up. I found better cover-ups. But if I look here at just the angle it's hard to move these little critters around. RPS is an inscribed angle, and its intercepted arc is RS. I also note that angle PSQ, from P to S to Q, is inscribed. S is on the circle, and its intercepted arc is PQ. So because I know arc PQ and arc RS are congruent, that's allow me to say that angle 3 is congruent to angle 4. I also know that measure of angle 1 plus the measure of angle 2 have to add up to 90 degrees, because we know that the acute angles of a right triangle equal 90 degrees. Okay, so that's some preliminary information I can get just from looking at my picture. That's essentially the geometry I need. From here, I'm going to do some algebra to solve for the different angle measures. I know that the measure of angle 1 was given to me. It's 6x plus 11, so I can substitute that in. I know the measure of angle 2, that was 9x plus 19, and I know that these will be equal to 90 degrees when added. I do my geometry or my algebra here, and I end up with 15x equals 60. X is therefore equal to 4. And when I substitute that 4 back in, I get the measure of angle 1. 6 times 4 plus 11, that comes up to 35 degrees. And then I can either take 90 degrees minus 35, and that would give me 55 degrees for measure of angle 2, or I could substitute it in and I could say angle 2 is equal to 9 times 4 plus 19, which equals 55. Whichever you choose to do will absolutely work. To find the measure of angle 3 and 4, I substitute in what I know about those angles. I know angle 3 is 4y minus 25. It's congruent to angle 4, which is equivalent to 3y minus 9. And again, when I do my algebra, I end up with y equals 16. And then I can substitute back into each of those, or even just one of them, because I know angle 3 is equal to angle 4, which is equal to, oh, pick your favorite, 3 times 16 minus 9, and that comes out to 39 degrees. So there, we've solved for lots of different angle measures using the inscribed angle that intercepts a diameter, and congruent arcs have congruent inscribed angles. Whew, had to think about that one for a moment. All right, let's look at yet another theorem, because this is fun. This theorem says that if a quadrilateral is inscribed in a circle, then the opposite angles are supplementary, which means that they add up to 180. So this one's pretty straightforward. If I look at my picture here, I have some preliminary things marked. This is an inscribed quadrilateral, 4 sides, and its opposite angles by this theorem are going to be supplementary. So Q plus S equals 180, R plus T equals 180, and you can substitute in for Q and S, all of which you were given, and you should end up with the measure of angle Q being 80 degrees, and you should end up with the measure of angle R being 85 degrees. And I'll let you do the substitution and the algebra to get you there for expediency. I think the next example actually a little bit more interesting because it combines a couple of different angle relationships. So if I look at this picture, the first thing I notice is that angle XOY is a central angle. And we haven't talked about that in a bit, but I'm going to label it. That is a central angle. And if you remember, the central angle and its intercepted arcs are congruent. That means arc XY is 90 degrees. I think I wrote that down over here. Mark of XOY, measure of XOY equals 90 degrees. And then I also notice that I have an inscribed angle here. So I'm going to cover up this part of the circle. I'm going to cover up this part of the circle. And I note that angle XZY is inscribed. Z is on the circle. And I know from one of my previous theorems that the measure of the angle is equal to half of intercepted arc. So if I do some substitution here, I'm going to be able to find the measure of this angle is is going to be equal to half my intercepted arc. And we know that that arc is 90 degrees because it's created by a central angle. And the central angle is a right angle. And so half of 90 degrees is going to be 45 degrees. So my measure of angle XZY is 45 degrees. Two different angle relationships. It's going to be important that you keep those in the forefront of your mind and ask yourself every time you see an angle, is it at the center? Is the vertex at the center? Is the vertex on the circle? And there will be some more that we're going to learn about, but that's for a different day. All right, another interesting example is example 9. And in this case, we have a hexagon inscribed in our circle. So what do we know about this? Well, I went ahead and drew a diameter. BE is a diameter. And I know the hexagon, it's a regular hexagon. I thought it said that somewhere. It's a regular hexagon break, which means that each side of the hexagon is equal and all of its intercepted arcs, or all of the arcs created by that hexagon, are going to be equal as well. So I did just a little bit of digging. I remember that I can find the measure of, or I can take the whole circle, 360 degrees, and if I wanted to, I could break it up into 6 equal parts. So if you wanted to think of this as a central angle, that central angle is 1 of 6, which means that its intercepted arc is going to be 60 degrees, right? And then if BE is a diameter, then the angle created by BFE is going to be a inscribed angle that intercepts this semicircle, and therefore this is to be a right angle. So I know that the measure of BFE is going to be half of my semicircle, which is 90 degrees. I'm going to put that over here. BF, ooh, look at me turn that into an F. So I know this is 90 degrees, and I know that each arc is 60 degrees. So you might be wondering, how does that help me? Well, I can figure out, well, we did figure out the measure of arc CD. We said that was 60 degrees, and we found this measure. We said this was 90 degrees, but now it's asking me to measure B to C to D, which is, whoa, slippery little fella, which is actually a, it's an angle. It's an inscribed angle. I know that because C lies on my circle, right? And so even when I cover it up, I really still have a lot of circle left. But we know each of these arcs is 60 degrees. So I can add all these up. 60 degrees plus 60 degrees plus 60 degrees plus 60 degrees is going to add up to 240. So if I know that arc, let's see, this is B all the way around to D. If I know BD is equal to 240 degrees, then I can use my angle relationship, and I can say that this angle, what was that, BCD, is going to be half of my arc, which we said was 240. Oh, look at that, it's kind of silly, 2 different colors. But anyway, BCD, therefore, is going to be equal to 120 degrees. You can almost see that from my big old arm being in the way. So that's how we can use the inscribed angle and its relationship to its intercepted arc to solve problems like example 9. Let's see, what else do we have in store? Oh, I think that's it. Oh, hallelujah. That's it, guys. So I guess you're just gonna have to stay tuned for another lesson at a different time. Thanks for joining.